CSC 224.
Okay, good evening. We're going to do test 4 review tonight, and that test will cover counting, graphs, and finite state machines. So what I'm going to do tonight is talk a little bit about some of the homework problems. So if you have questions on that, I'll be talking about some of the homework problems, and we'll just be going over some of the general concepts in counting, graphs, and finite state machines. And I'm going to start with finite state machines because I think that gives people a little more trouble than some of the other things. Partly because I didn't spend a lot of time on it, and you haven't seen a lot of examples. But what are some things that you need to have in a finite state machine? Like if you look at a diagram, say you're a grader for a class like this, you look at a diagram, what things, if they're missing, would you mark off for?
Transitions.
Well, you need some transitions, okay, but what else do we need? We need a start state. So you have to have a start state, and you have to have what? That's sort of the mirror of this. You have to have an end state or an accepting state. That's what I usually call it, because you can end in other states, right? This is usually called a final or accepting state. And we need to have, so we have nodes, right? So we have a set of nodes, and we have transitions. And that's pretty much all we need in a finite state machine. And then if we want it to actually work the way we want it to, it has to have other stuff. But there's not something in general I can list for all the possible finite state machines that will ensure that they will work. But what's one thing that you don't want in one if you don't want it to be non-deterministic? What does non-deterministic mean? This is one of those words. Do you guys remember taking test 2 and I told you were in trouble if you didn't do the Fibonacci problem?
Yeah.
This is one of those things, if you look at the word and you freeze, you shouldn't, because you just should think about what this word means. It says non, okay, so that means opposite, so you can ignore that when you're figuring out what it means. Deterministic, like that looks like the word determine, right? So deterministic means you can determine what will happen. Okay? And non-deterministic means you cannot determine what will happen. So that means there's something in the diagram that has some kind of random jump. That means there's a transition somewhere that you don't know if it happens or not. That means it's usually labeled with an epsilon or nothing. So if you have two states and there's an arrow between them with no label or with an epsilon on it, epsilon means nothing. Also, you can write it as lambda. Okay, that's non-deterministic. So if you have any of those in your diagram, that means that if someone's trying to write code for your finite state machine, they don't know what to do at that point. They have to put in a random jump between two states. And that's not good because you can't write a regular expression for that either, right? So you don't want things that you don't know what happens, because normally you want your programs to do just what you tell them to and nothing else. So you want to get rid of these, and I'm not going to go through how to get rid of them. I'm just saying don't design them in the first place with them if you can help it. If you can't help it, that's fine. You can put them in if you need to. Okay, so let's do a few examples. What's one of the homework problems? Like part A. We had A star, B star. One thing that might help when you're making these diagrams is to think about what are the possible strings that would be accepted. Because that helps me check my finite state machine. That's actually the first kind of thing I start thinking about. Instead of thinking of states, I think, okay, what kind of strings are in there? So the shortest string is the empty string accepted? And the answer is yes. Right? So that means which state should be an accepting state? The start state should be an accepting state, right? So that's one of the strings. Just 1A is one of the strings, right? Just 1B is one of the strings. So I'm just starting to list the language here. I can get 2 A's. I can get an A and then a B. I could get 2 B's. But what can I not get?
BA.
So BA is not allowed. So that's going to be one of the things I should check when I draw my diagram. Does my finite state machine that I drew, does it accept BA? Because if it does, that's a problem. So one thing that you do when you make a finite state machine is you want to make it so it accepts what you want, but it doesn't accept things that you don't want. So we want a start state, and you always need to label your start state. It needs to have start, and it needs to have an arrow going into it. Because sometimes these diagrams get really big. So you need to have a word start and an arrow so you can tell what's going on. So here, I might make a state and call it A. That means I'm in my A's, right? Because when I look at this, I also think, okay, this is a string of A's followed by a string of B's. What's that little star mean?
Zero or many.
It means a string of these letters, 0 up to however many you want, right? Okay, good. So if I get an A, let's say I'm going in a string of A's. So my A state is like I'm just getting A's. So what should I do to represent getting the rest of my A's? Make a loop that goes back into the state, because I don't really change what's happening if I get more A's. If I just look at this in a finite state machine, I think of this as A+. Right? That's getting guaranteed to get one A and then as many A's after it as I want. Okay? So this state is an accepting state, so I need to make a circle around it. 0 is sort of the state that it was, and then it's an accepting state because we accept epsilon. And we also accept any string with just A's, right? What happens if I get a B if I'm in the A state? What do I need? Another state, right? Because I don't want to go back in this state, because then if I get more A's, I'm going to accept that, right? So then I would accept ABA, which is not in my language. So I need to make a new state. And that's an accepting state, right? Because AB is a valid string. And then if I get more B's, I stay here, because I'm allowed to have as many B's as I want. There's only one thing missing in this diagram. What is it?
Start to B.
From the start, I can go to B with what transition? There's an arrow. And what's the letter on it?
B.
B. So there's the simplest finite state machine we can make for this. Yes?
Could you collapse the A state into the start state and just put an A loop on the start state?
That's a really good point. This isn't a minimum state, right? Because you're right, I could collapse these two. That's a really excellent idea. So instead of this, I would just put start right into the A state. And then B already goes to B state.
Question.
Okay? Yes?
Why would it go from the start to the B? If you look at your string, it's A star, B star. I mean, does that mean it always starts with an A?
No, it starts with a string of any length of A's.
So you could start your string at B.
I could start with B. So one of the strings we listed as being possible is just a B. Right? Because the star means any number of them. It's just a way to write any power, and it could be 0.
I didn't get. Did you say you could start with B and not A?
That's right. The first character I get can be a B, because a string of just B's is okay. Because A star means 0 up to any number of A's. Okay?
So then could you really collapse and start with A? Wouldn't you also have to have a start going into B?
No. Because if this were the start state, then I would already have an arrow going to the B. So that simpler diagram looks like this. Right, so this accepts epsilon. It also accepts any number of A's. If it gets a B, it accepts any number of B's. But if I try to put BA in, it doesn't work, right? So I'm in this state, I get a B. If I get an A, I go nowhere. So if you want to draw like every possible thing that can happen, like getting an A here, I would add a final dead state, like wrong string, and have an A going to that. If I wanted to list all the possible things that could happen, I would make another state and say, this is bad, okay? And have anything I didn't want to get go to the bad state. Yes?
Is the reason that you don't have 3 circles on your right-hand side is because going into the start state, you can't accept a B. And see on your other one, you have 3 circles.
Yeah, 3 states.
And that's saying that you can accept A, B.
No, that's a 0.
This is a 0 inside. So there's 3 states here.
Okay.
This is the start state with a 0 is the name of the state. You put the name of the state on the inside.
Okay, I was looking at it as an A and then a B being able to be put in
I see
there.
what he's saying. I mean, with the second diagram, you can't start with a B because your start
You
always
can.
starts in A.
You can
start
because
with B.
this start means this is what state I'm in.
Oh, okay.
So I
This is
wouldn't
the
call
state
it
like
A anymore.
So it's A
might
or
label it 0.
blank.
right.
Okay.
So I mean, both of these are fine. I didn't say you had to have the most efficient finite state machine ever. Okay,
Just had to be right.
it just has to be correct. If you had 15 states, it would be fine. I mean, Andy might mark it wrong, but if you came back and it was correct, I would mark it right. Andy's much more quick to go, this is wrong. But, I mean, that's not bad because it's clear that if you have 15 states in this case that you're doing a lot of extra work, right? You need to work on your finite state machines if you have 15 states. Okay, let's do some more.
So what's the state table?
The state table?
Yeah.
Okay, we can make a state table for this. Let's do it for the simple one. Okay? This one is, we have 2 states, right? We have the A state and the B state. So I label a column with states. And these are my letters that I receive.
What about epsilon? You don't need to put it.
No, if I don't put any epsilons in my finite state machine, I don't need them in the transition diagram. So I don't put them because I don't want any epsilons in mine anyway. Epsilon should leave you where you are. Okay, if I'm in the A state and I get an A, where do I go? A state. If I'm in the A state and I get a B, where do I go? The B state. If I get a B, if I'm in the B state and I get an A,
Yeah.
here I would really ignore this because I really wouldn't put this on this diagram. Okay?
Do nothing.
So this would just do nothing. You know, that's a non-accepting thing. So you don't actually even go back to the B state. You just do nothing. That's right. The finite state machine just dies. Wouldn't you love it if your computer programs did that? That's why it's actually good to add this state. So it doesn't hurt to have it in there. Because then in your computer program, you know what kind of output to get. If you ever go into the wrong state, you could print out a statement that says, you have entered an invalid character. Right? That doesn't necessarily help them go back and fix anything. At least it tells them, though, that they did something bad. Okay, and if I'm in the B state and I get another B, I stay in the B state. So it's a little bit confusing to have the states labeled with the letters, but it's okay. Okay, I might like put circles around them or something so I realize that those are the states and not the letters. And one of the students I was working with before class was writing in each place like what kind of string he had gotten so far. Right, so you could make a list of what, also in this, if it helped you, you could make a list of what kind of strings you had gotten and what you should be accepting in those states. But that's not required for a state transition diagram, which is what this is. Because it tells me what my transitions are, which state I go to if I'm in a state and I get a letter. Okay, everyone ready to try another one? Yes, yes, yes.
Do you ever need to handle the empty string? Do you ever need to do anything about it, or?
That's a good point. In this particular problem, we had the empty string was okay, right? And one thing I might have done in this diagram is, written here that this is a final state and this is a final state. And I also would have written that this is a start state. And if I had done that, it would have been clear from my diagram that getting epsilon leaves me in an accepting state. So that's a really good point. You need to write which ones are final accepting states.
So according to the simplified diagram, it must have A. It cannot only have B in your result.
No. An empty string is okay. So here, being in the start state, I don't have to get something to get here. This is an accepting state. So when, like, say I implemented a finite state machine with a piece of code, okay? And if the code, if I like sent it an empty string, it would come back and say, okay. Because its initial state, like if you haven't touched it, it's accepting.
Okay, but from the start, the first things must go to A. You cannot from start go to B directly.
Okay, that's the problem with label these with letters. Okay, this is the one state. Let's just think of these as numbers. This is the one state, this is the two state. You can label them with letters, but calling it A doesn't mean that I've got any A's yet. It means I got an A or no A's. It means I haven't got any B's yet. That's why we called it A. But you can call it 1 and 2, and that it doesn't have anything to do with what actual letters you've got. It's a notation. If you call it with letters or a string, it's a notation that helps you remember what happens there. Okay? So this does not require me to get any input in order to accept. If I'm in state 1, which I am because it's the start state, then the empty string is an accepted string in my language. Okay? So the only time you're going to have an empty string as accepted in your language is if the start state is an accepting state. Right? And if you have, like, if everything in your regular expression has stars on it, then the empty string is in your language. Right? If everything has a star on it, that means you could have 0 of everything, which means you have a string of length 0. Okay. Right? That star stands for a number, which is the length, which is the number of those characters that you get.
So from this diagram, it could start from 1, also could start from 2.
No. Start tells you what state you start in.
But in your final results, it also include B only.
That's right. B only starts in the start state, gets a B, and goes to the 2 state.
Okay.
Okay?
Okay.
Sure.
Good.
What about if only has B without star? A, B star. You have to start with A, or you also
No,
can start.
this diagram doesn't require me to start with an A. Okay, that's the problem with simplifying a finite state machine. Okay, go back to this other example. This didn't get any input to get into the start state. Neither does this. Just because I collapsed them doesn't mean they're any different. I get into the start state no matter what. I haven't got any characters when I get into it. I don't get characters unless I move. I move somewhere, I go on an edge. Going on this edge is an epsilon technically, but the start just puts you're just labeling which state the machine is in. It's like vending machines have finite state, something equivalent to a finite state machine in them. Okay? So if you just leave the vending machine, it should have a start state in there that says, okay, I have, I'm fine. I'm at the balance is good. Right? Now, if I start putting money in, it has some other state that says I've got a certain amount of money, and if they give me enough money, I'm going to be in the give some cans out state. Right? But that start state is accepting. And so is a nickel state, and a 10-cent state, and so is a 25-cent state. It's fine. It's going to continue. Those aren't accepting, right? Because it's not going to sell any drinks yet. The start one's not really exactly accepting either, but it's an okay state to be in. It doesn't really want to be left in the nickel state, though, right? And no people ever leave a machine like that unless they have to. Okay, so the state it starts in is a valid state, and you don't have to get anything to get to it.
The state that accepts epsilon.
Yeah, it's like it's the state that takes nothing. Okay? That's why we have to label our start state. Otherwise, we wouldn't know what to do with this diagram, right? We wouldn't know what to do with epsilon. And in a finite state machine also, if you don't know what to do with epsilon, you do nothing with it. If it's not labeled, you don't do anything with it and it's not accepted. So if the start state's not an accepting state, the epsilon is not accepted, right? Okay, let's do another example. What's the next problem?
A or B. Okay. B star.
Okay, I think what part of the problem is that you're not used to thinking like computers yet. Okay, you will get used to it because you have to do it a lot. Computers only do what you tell them to, and they do nothing else, absolutely nothing else. So if a program doesn't work, whose fault is it? Yours. It's the programmer's fault.
The computer.
It is not unless it's Windows, okay. Just kidding. So, you know, if the computer crashes, it could be your fault, but it might not be. But if your program is not doing what you wanted it to, it's because you did not write it correctly. Okay, and there's a huge area in computer science of validating code, checking to make sure that it does exactly what you wanted it to. Finite state machines are a way to ensure that you make code that does what you want it to. Because if you could make a case statement that says, if I'm in this state and I get this character, go to this. And that's it. And you just want to program that. And then if you have a diagram that tells you whatever state you're in, whatever character you're in, and you know what to do next, then you've fully explained everything you need to do in your program. Right? And then you can double check your program and make sure that it does exactly what the diagram says, which is why finite state machines are useful. So in this case, this says this plus right here is not the same as the plus in the power, right? What does this plus mean?
Or
It's an or. So either A or B, but not both, right? It's not a string of A, B. It's A or B, getting one character. So the length of this is one character. What's the length of this?
0.
0 or any number, right? Okay, what's the length of this?
1.
So another way to check that your finite state machine is correct when you do this is to make sure that, say you make a finite state machine that has 5 states, and there's a transition with a letter on every edge. Would that be one that would work for this? It wouldn't, because if I have a finite state machine that has a start and has 4 transitions, before it accepts anything, can it accept a string with length 2 if none of these are epsilons? No, but a string of length 2 is in the language, right? So this can't be correct, no matter what you do with it. So as long as you're not allowing it epsilons. So if we don't want any epsilons, this cannot work. And we don't want any because this is a regular expression. We don't need to use epsilons. So we want a state that takes one character, then takes any number of B's, and then takes an A at the end. So I would say that probably needs 3 states, right? Plus a start state. So here's my start. And then I need to either get an A or a B. And I need to change states because that says I've sort of gone this far in my string. That's how I'm thinking. When I'm making a finite state machine, I'm going through this string and seeing, have I covered that yet? And then have I covered that? Have I covered that? That's what I do as I go through. So this, getting to this point in this string is what the one state is for. Now, if I get some B's and do like that, that also covers me, right? But I don't have to get any. If I get an A next, I can be done, right? In the 2 state, though, I'm done. I don't want to get any more characters, so I don't draw any edges going out of 2.
Wouldn't it be also possible from the start state to have one arrow going to the A and then one going to the B?
Yeah, you could have 2 arrows, one labeled with an A and one labeled with a B. So I could put A on one arrow and draw another one down here and put B on it. Or you can put commas on them. I like to put commas just because if you get more complicated diagrams, it's harder to read if you put more arrows.
No, what I mean, 2 different states. One A going to one state and one with B going to a separate state.
I could if I wanted to. I would do that if I wanted to somehow specify something to do if I start with an A and something to do if I start with a B. That would be a reason to do that. In terms of just representing this, though, I would just say, okay, here's a state. I either got an A or B to get here. So you could do that. You could start with 0 and say A goes here, and B's stay right there, and then an A takes me here. And then it would be an exactly identical finite state machine, except you would have states for two different states for getting either an A or a B, right? So it's like making a copy of the rest of the diagram if you do that.
It's not
But I wouldn't want to do it
yeah,
because
it's not
that's more
incorrect.
states.
It's just
It's not incorrect, so that's okay.
Yep.
So in code, what kind of statements would you use if I were trying to code this?
Switch.
if, else, switch.
Like if, else, or switch, or case statements, right? So, and you would be getting characters sequentially. So I'd get a character, look at it. I'd look at my state. I'd look at the character. I'd say, okay, and I'd look at my state transition diagram, say, if I have this state and this character, what do I do? And I do that. And then all I have next is a state that I'm in. And then I get another character, and I do the same thing over and over again. So a program to implement a finite state machine is easy to write, right? And it's easy to check. That's why we have them. Okay, so how about the transition diagram here? So this one's a start state. And do we accept epsilon?
No.
No, we don't. Oh, sorry, that was the start state. So 0 is the start state. If I'm in the 0 state and I get an A, I go to the 1 state, right? If I get a B, I go to the 1 state. If I'm in the 1 state and I get a B, I stay there, right?
Mm-hmm.
If I get an A, I go to the 2 state. If I'm in the 2 state, I don't take any more inputs. So if I wanted to label, like going to a state for that, I would put a wrong state and arrows that go there if I have any inputs after I get to the 2 state. But usually when you're talking about finite state machines, it usually assumes that you're starting a new problem after that. But, you know, after you've accepted, the machine will go back to the start state. Yeah, it might print out something good or accepted or something, and then go back to the start state after that. So let's do a counting problem. How many different strings of length 10 are in this language?
In this language. This one right here.
In this language right here.
There's different strings.
Yep.
Choose one.
2.
So we have, if it's length 10, it already has to have this A, right? And this is 1 character, so how many B's do I have? 8. So I have 8 B's. And I end with an A, right? And the first one either has to be an A or a B. So there are 2. This is my diagram. I put a blank, and I have 2 choices in that one. The rest of them have to be like that. So there's only 2. So it's an A followed by 8 B's and then another A, or 9 B's and then an A. So that was kind of like what I did. I checked what length strings I should be able to get. So that told me that in 2 jumps I should have been able to get to an accepting state, and I could in my diagram that I made. And it also told me that epsilon would not give me a final state, right? So it tells you a lot of things if you look at the length of how many things you can get.
What was the first thing you said? It tells me.
This tells me that since there's a minimum of 1 character here in A plus B, and there's a minimum of 1 character to get my last A, that the minimum length string is 1. So epsilon isn't going to work, and any string with length 1 is not going to work. So it tells me that I I have to have two transitions that will get me to the final state. I'm just giving you ways you can check what you're doing. So there's lots of ways you can do it, and you can just pick whichever ways you like. So we had a problem on one of the old homeworks, on the counting homework, where we had to count. We had strings of length 10 with 5 consecutive zeros or 5 consecutive ones. Let's just solve the 5 consecutive zeros problem. Okay, and our language is what? It's 0, 1 star, or you could put 0 plus 1 star. All right, that's the way you do that. So it's bit strings. So that's the characters. Like, it's our language is a subset of this. So this is our, overarching. We're looking at bit strings. So for length 10, like most of our finite state machines, they have to have, if we want an exact length, we have to have that many transitions, right? Because otherwise we can't count how many things we get. So let's look back at our last one. This doesn't limit how long our strings can be. If there's any stars in there, right, if you put any loops, you can get any length that you want. Like this is minimum 2, and then I can have any other length possible. So it's good to be able to count those. So I'm not going to be able to have any loops in this, right? So it's not a beautiful finite state machine we're going to come up with, but it will work, right? So how do we draw our picture before for accepting these? Before, when we solved the counting problem. We said we had 5 zeros, and then we had 5 blanks, right? And that was one of the ways to do 5 consecutive zeros. And then we put the 5 consecutive zeros starting in the second position, which means we had to have a 1 in the first position. So we only had 4 blanks in that one. And then we sort of just shifted that over down the string. So I have, the last one was, that should be a 1, 4, 5, 6, 7, 8, 9, 10. So those are all the possible things that we had, right? And there were 2 to the 5th of this one, because I have 2 choices per blank, and there's 5 of them, and the rest of these are 2 to the 4th because there's only 4 blanks. So the total was 2 to the 5th plus 5 times 2 to the 4th, right? Because there were 5 possibilities with 2 to the 4th. So that was just to remind you how we counted that one, because we had to draw a good picture of how they don't overlap. But that picture could also help us figure out the finite state machine, right? So we need to know, like, when do we start getting those 5 consecutive zeros, right? Okay, so we'll have a start state. And if we get a 0, we might possibly be in this state, right? If we get a 1, we're in any one of the other ones. Or 0 could either also be one of these, right? Okay, so I have a feeling this is going to be a big diagram. So we have a start state. If we get a 0, we go to 1 state. If we get another 0, we know we could still be in the first state, right? We need a counter. That would be nice, right?
Well, you'd have to be in the first state, wouldn't you? if you got
Oh yeah,
another
for
zero.
this, yeah, I'm just drawing what it's like to be in the first state. Now what I could do is have this be my string of 5 zeros. Then I can go to all the possible start things that I could do before it and then send it here whenever I think I'm starting the zeros, right? So I could do all the other possible starts and then do that. So how many possible starts are there? Well, I could start with a 1. And then I have, that's 2, right? There's one possible start like that. There's 2 here. There's 4 here. And then 8, right? And 16. So I don't actually want to draw that, right? This is what finite state machines, I'm showing you how they aren't going to solve all problems for you, right? They're easy to code, right? But you don't want to make a finite state machine like this. You want counters. I don't want to draw that many states. 1 plus 2 plus 4 plus 8 plus 16. That's a lot of states. And then I still have to do the stuff after, right? I haven't even done that. So what you want to do in that case is you would want to use something more complicated than a finite state machine. But if you wanted to do it, you could do it, right? You would just take a lot of paper. So, and actually, you couldn't even use this state. You just have to copy this for all of them, because what happens is, if I were to do this one, then I need to do 4 things after it, right? And if I do this one, I have to do 3 after it, right? So I would actually have to have kind of like a path in the finite state machine for every different string, right? I'd have to have this many sort of paths. So I'd have to have this many strings of zeros, like this diagram that I have right here. Because I don't have a counter to keep track of how many things I've done so far. So Van, did you have a question?
I was going to say, what happens if you get 6 ones in a row? Do you have like an error state? Is that an error condition?
Well, that would be a non-accepting state, right? So if I got 6 ones in a row, that would just dump me out. Okay, so this is a problem that you don't want to solve with a finite state machine. You would want to use a counter, right, or something like that. Okay, does anyone want to work some more finite state machine problems? Or we can move on and talk about counting and graph theory. So we've been doing a little bit of counting. So what kind of problem was this problem? Does order matter in this problem?
Yes.
What is your clue that order matters?
Series of 5.
There's a word in there that's a clue.
Second.
String. String means order matters. Because a string is an array of elements that have order. That's what a string is. So anytime I see the word string, that means order matters. Now, if someone says, how many strings are there, when order doesn't matter, then you assume it doesn't matter. So, but if you see the word string and no other indication, then order matters. Right? And a range also implies that order matters, right? Yes?
Yeah, I've got a question on the B plus in bracket B, A and B star. So I've got a question of A and B star. How do we represent that?
Okay, we can do this one quickly, but we're not going to spend too much time on it, okay? B plus AB star. So we can have strings that have just B's and nothing else, right? Because AB star means I can have 0 of them. So we know that we need a state that accepts, after we get at least one B, then we accept any number of B's. So we know we have a start state, but we can't accept epsilon, so that's not a final state, because a B plus means you get at least one B. So we take one B, and we'll go to the 1 state, and that needs to be accepting. And then B plus, like I said before, making a plus always looks like that, right? You get a transition with the letter and then a loop with the letter repeated. That's always what that looks like. All right, now, if I get A, B star, so I know if I get an A, I'm not in that state anymore. I got to go somewhere else. What happens if I get a B? Do I want to go back to the 1 state? No, because I don't want to be allowed to get some more B's. I should go to another state. And that's a final state because BAB is an accepted string, right? Now, what if I get an A in state 2? Don't do anything. So you could send it to a wrong state or just leave the diagram as it is. What if I get an A in state 3? Let's go back to 2. Because this allows me to get another AB. So B in state 3 would be bad. I don't allow B's from state 3. But in state 3, I can get an A and get another B and be back in state 3 again. So state 2 is kind of like, okay, I'm all right, except I've got an extra dangling A. And if I put a B with it, I'll be fine. So when I'm thinking of these states, I think of it as a place I'm standing, and I'm allowed to do certain things from there or not, depending on what the transitions are.
And in state O or 0,
0?
are you allowed to get A?
No, because I have to get at least one B, right?
Right, okay.
So getting an A in the start state would send you to the wrong state, right? So if we had another state on there, that would catch all of the things that are not allowed. Yes?
Now, once you hit the parentheses, do you have to have an A there?
No. So the parenthesis is not something in your string. A parenthesis pairs things together. It's kind of like in addition. Like, I don't really need to read the parentheses in the number. So it just means you do the stuff inside the parentheses. So if I get a B, I'm reading this. If I'm reading a string that's in this language, I don't have any parentheses in it. So strings that are in this language look like this. B, B, A, B. B, A, B, A, B. Also, any number of B's and any number of ABs.
So that A right after the first B must be there.
If I get any A's, I have to pair it with a B.
Gotcha. That's what I was really asking.
That's what this means. Since they're stuck together, if I get an A, I have to get a B also. That's what that star on the outside means. It means you get an A, B, and you get them together whenever they're in a package. Okay, and I'm not going to do the transition diagram for this because you can read it off of the finite state machine, right? The reason why I had you do it on your homework is to practice. Because you can write code from a transition diagram, with the table. You can write your code from that. This picture helps you make sure that you're doing everything correctly. Because a table is very hard to read the whole thing, right? Here, it's easy to go through a sequence of letters and make sure that this is accepted. You can test things with the diagram, with the finite state machine. So I think that you're probably hearing enough from me about the importance of being able to test things, right? I mean, especially even with little pieces of code, you've got to be able to test your inputs. You don't want someone to come use your program and type things in that you don't expect, right? Or you want, like if you make these things, I would always, like if you're actually coding them, I would put a wrong state in and have something to do whenever that happens. Because you want to give feedback to people and let them know that the program's not going to do anything else. Okay, so we were talking about counting and things that like string or arrange. And also, if you have prizes, these tell you that order matters. And if you have a question in your mind when you're solving a problem, what should you do? You can draw a picture. And then in the picture, you can decide if order matters. Now, the other thing that I would do is think to myself, does it matter which prize I get? And if it matters, then order matters, right? Also, write down your assumptions. So if there's a word in the problem that you're not sure if it means order matters or not, just write down. It says, I assume that order doesn't matter in this case. And then you solve the problem. And if you think, Tiffany probably thinks order matters, then you should solve it both ways and say, if order matters, this is the answer. If it doesn't matter, that's the answer. Because then you've covered all your bases. You get maximum partial credit that way, right? But of course, if it was your job to calculate these things, you don't want to be like, well, if order matters this, if it doesn't that. You would write down your assumption and you would say, this means that order doesn't matter, and this person said that, and that person said that, so I'm going to solve it that way. Okay? So we write our assumptions. So what are kinds of things that order doesn't matter? Do you care what order your donuts come in? No. How many ways are there to choose a committee? You know, committee members are all considered equal after you choose them, right? So if there's something that's considered equal after you choose it, and it doesn't matter which one got chosen first, then order doesn't matter. So that's really like right in there. If it doesn't matter what order you choose them, then it's a combination, right? So these are permutations and combinations. So pretty much if it's not a permutation, it's a combination. So order does not matter. So let's see. Let me do some examples. So if we have a set, the elements are 0 up to 7, and we have a language, S star, then how many strings of length 5 are there in S star?
Oh, wait. 2. Wait. S.
S star just means any ordering of those letters. Any number of any of those repeated over and over and over again.
7 to the 5th.
So I have 5 blanks, right? Because it's a string. And as soon as I draw blanks, I'm pretty sure that it's going to have order matters. Right, so if I can write my problem where I'm drawing blanks, unless I'm labeling the blanks and then choosing one of them, which I sometimes do, then it probably is an order matter problem. So in this case, how many choices do I have for the first one?
8.
8 choices, because 0 goes up to 7, right? So 0 to 7 is the choices here. How about here? 0 to 7 again, right? Because I didn't say I couldn't use the letters over or string numbers over again, right? So all of them have 8 choices. So the answer is 8 to the 5th. So you don't forget which number is which. The number you're choosing is going to be in the power. And is this with or without replacement?
With replacement.
This is with replacement, and can someone explain what with replacement means?
You can use them over again.
I can reuse the elements in the set that I'm choosing from. So what with replacement means is I always think of it as having a hat where I make my choices out of the hat, and after I choose a number, I stick it back in the hat, shake it up again. So that's what with replacement means. I replace the number I drew out. So when I first did counting, I thought that was very confusing, with and without replacement. But it's not. It's just a long word. It can be confusing to figure out whether a replacement is allowed in a problem. So if you're not sure, you write down your assumption and why. Why did you assume that replacement's allowed? I did here because they said strings of length 5, and strings in most languages I know are allowed to have more than the same letter used again. Right? We wouldn't have English as big as it is if we weren't allowed to reuse the letters. So how about
Can you do a question on homework 9?
sure, if you have a question you want to solve related to this,
Was question number 7, I don't know.
you can read it to me. That would be great.
Let D be a positive integer. Show that among any group of D plus 1.
I know the problem.
Consecutive integers.
Okay, if we have D is an integer, and it's positive, So it said show that any set of d plus 1 numbers not necessarily consecutive what?
There are
There are two with exactly the same remainder when they are divided by d.
What is the binary relation that looks at remainders?
Congruent mod.
Congruency mod something, right? So I have to show that there's two numbers x and y mod d that are congruent, right? So another way to write this problem is show that in any set of d plus 1 numbers, that two of them must be congruent modulo 1 less than the number of things in the set. So that means that, let's say I have three numbers. So two of them have to be congruent mod what? 2, because that's 1 less than the number of things in the set. And is that true? Yes.
Yeah.
The modulos are 1, right? 1 and 1. Actually, all of them have it, but I can prove that they have 2 with what?
Pigeonhole.
The pigeonhole principle, right? If I have only 2 remainders, I only have 2 choices in each thing, right? It could have been 1 or 2, 1 or 2, 1 or 2. I've got 3 of them to make, right? So all of my possible strings would have been 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, 2, 1, 1, and so on, right? So all of them have at least 2 of something that's the same. They could all 3 be the same.
Where did the 7, 25, and 13 come from? I didn't catch that.
They're random numbers. It's a set of 3 numbers. This was an example. This is not a proof, right? It's an example. So let's do a proof. So there's a key word in pigeonhole problems that helps me figure out which ones are the holes and which ones are the pigeons. What is the key word?
Same.
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 That's right. The key word is same. If you see the word same, the thing that comes after that is the holes. Because in pigeonhole problems, you only have to figure out what the pigeons are and what the pigeonholes are, and then you're pretty much done. As long as there's what? More pigeons than holes. Okay? So if that's not the case, then you have to do some other work. Okay? In this case, we have this many holes. However many remainders there are, that's how many holes there are. So if I divide a number by d, how many remainders are there?
2.
Well, if I divide by 2, there's 2 remainders. If I divide by 3, what are the remainders? 0, 1,
And 2.
2. Is 3 a remainder? No, because if I divide by 3, I go ahead and divide that one out too. So 0 is again my remainder, so it repeats. Every number is 0, 1, 2, 0, 1, 2. So consecutive ones, if I had any set of consecutive ones, numbers always go like this if I divide by 3. So any set of 4 consecutive ones will definitely repeat no matter where I do 4 consecutive ones, right? But we said not necessarily consecutive, but that's okay, right? Because we only have however many d is, that's how many holes we have. So we have d holes, right? Because the possible remainders are 0, 1, all the way up to d minus 1. That's the possible remainders. And I have, the other thing is pigeons. So the d plus 1 numbers is the pigeons. So since I have d plus 1 pigeons, by the pigeonhole principle, there are 2 pigeons, or numbers, right, because they were numbers, with the same remainder. Because 2 is actually, that's equal to d plus 1 over d, the ceiling of that. Right? So we have d plus 1 numbers and only d remainders to give out to them. And since d plus 1 is bigger than d, then I can guarantee that 2 of them got the same thing. And remember that solving this problem, we can also remember if you started handing out distinct ones, as many as possible, you would have handed them all out and you would have had to give somebody the same thing. Again, because you don't have anything else to give them. And everything gets labeled. There's nothing that doesn't get a label. Okay, so that's a pigeonhole problem. We have a few things that we have. We have combinations with and without replacement. We have permutations with and without replacement. And we have graph theory also, right? And we just have a few things in graph theory, but we're sort of used to it because we drew a lot of graphs with binary relations, right? Okay, so in the pigeonhole principle, we just did an example problem of that. So the only thing that you might have to do is what? So if you have n pigeons and k holes, you're always going to be able to guarantee that that many pigeons have the same hole. So that's why you look for this word same in your problem, because it tells you where the holes are. So sometimes you have to figure out what some minimum for n is and what a max for k is, right? But you can try those by hand. I'm not going to give you a problem that you can't, like, just start filling. What we did? We just started drawing boxes, right, and filling them the sort of most even way to help figure out the numbers. But that's not the only distribution, right? We can distribute any way, but the pigeonhole principle works on the minimum number per box distribution, right? That's the one that shows us all the numbers the nice way. Okay, so how many socks of different colors do I need that means that's a minimum, right? To select 2 with the same color. And you guys who don't like to match up socks in the laundry, like if I'm picking 2 at random, or like how many socks of different colors do I need? That if anytime I pick 2 of
One more than
let's see, how many socks of different colors do I need to select 2 of the same color?
Socks?
I'm not writing the problem correctly. What?
How many different color socks?
Yeah, if I select 3, if I select 3, and I want to guarantee that 2 have the same color,
And you can only have 2 colors.
and guarantee so that's a maximum number of socks, right? So the word same comes before the word color, right? So the holes are colors. If I make 3 selections, what's the only time if I have 3 socks, I have to have some number of colors equals 2. I'm guaranteeing that 2 of them have the same color, right? So that's what the pigeonhole principle says. Well, 1 color doesn't work, right? Does 3 colors work? No. Does 2 colors work? Yes. So sorry I wrote the problem badly, but so if you have 3 colors, if you have 2 colors of socks only, all you have to do is pick out 3 and you always get 2 that match. And then you can toss the one that doesn't match back in the drawer. So if you have 2 colors of socks, the maximum number of times you'd have to choose socks to get 2 that match is 3. That's a good kind of problem to be able to solve, right? If you want to guarantee that you have some certain number of things, you can figure out what the max number of choices you'd have to make it. That would be the pigeons. Like, so if you know how many colors you had and you want to guarantee this number, you could figure out how many pigeons you would need. Right? So another way to write this problem is if I have 2 colors of socks, how many choices do I need to make to guarantee that I get 2 that have the same color? So the pigeons are the choices and the colors are the holes. So you could have figured out 3 from this if I told you that this was 2 and that was 2. Okay? So for practice at home, it would be good to just try rearranging like which number you do and don't know in this problem. Okay, and change this number for practice. Okay, so there was only really one tricky problem in the counting, right? The tricky one was the divider problems. And also tricky ones are ones that you have to do more than one step, right? I have to do one thing and then do another. Okay, but you're just going to have to like practice and look at those and see what you need to do. So what is a divider problem? That's a combination with replacement, right? That's the only funny one. The rest of them are straightforward. Permutations with replacement were like making strings where I was allowed to use the same thing over and over again, right? Like we had 8 to the 5th was strings of length 5 in the language 0 to 7 star, right? So that was a permutation with replacement. So that was that's going to be n to the r. And then you know your formulas for PNK and CNK, right? These are without replacement. These are the normal ones on your calculator. So what's the formula for PNK?
Factorial
Over K for 2.
over n minus k.
Minus K.
So if you forget these, you can derive them by doing what?
Drawing pictures.
Draw a picture. Right. So I draw a picture. I make k choices, so I draw k blanks. And the very first choice I know has n choices. Right? And I just keep going labeling down until I run out of blanks to label. And then I multiply those, and it ends up being this. So if you forget the formula, you can always derive it. And then the combinations, all you have to do is divide the p and k by something. What is it? We're dividing by all the orderings of k elements,
PKK.
which is pkk. And just by drawing a picture, you know that pkk is just k factorial because your last blank only has one choice left. The first one has all k, and by the time you get to the last blank, you only have one choice. You have to put that one in there.
That should be equal to n factorial over k factorial times n minus k factorial.
That's correct. So it's the same formula as p and k, only it has a k factorial in the bottom also.
Can you pull that up a little bit? He's saying that that's the same as the one above.
This is c and k,
Okay.
which is the same as p and k, only has an extra factor in there. Because I had to divide the order out, because orderings make it more, right? So the only one that you can't do like this, like draw this kind of picture, is the divider problem. Because the divider problem was tricky. We mapped it into a bit string problem instead of one of these, drawing blanks and figuring out how many choices I have per blank, because it doesn't work, right? The reason why it doesn't work is because, say I'm choosing donuts, and I've got 3 kinds of donuts, right? I could choose no chocolate ones, and 5 plain and 5 raspberry, and I would have 10. But then I could choose 3 of the first 2 and 4 of the last one, and there's just not a good way to figure out how to choose each number, because the number remaining have to add up to 10. And that's what's hard, and that's why that finite state machine we had before was a big diagram. And that's the same kind of diagram we would have here if we wanted to do, say, 10 choices, you know, getting 10 donuts, and the whole thing has to add up to 10, and I can have any number of anything I want, right? So that's why we converted this into a problem where we said, okay, we have an order ticket, and then each kind has like an area, right? So say that I have 4 kinds of donuts, right? And the problem might be, how many ways are there to pick 12 donuts? So how many different dozen boxes? And in this case, you know, order doesn't matter because I wouldn't consider it different if I had the same number of each, because I can't tell my donuts apart. That's why order doesn't matter, because I can't tell them apart. So here, all I have to do on my order ticket is now I just have to put hash marks, right? Or put zeros for the donuts. So I have to draw how many zeros on my paper? 12, right? I just have to put them wherever I want them. So this would be, say, chocolate, raspberry, plain, and
Strawberry.
what?
Boston cream.
Boston cream. Okay? So we got all the best ones, right? So you could just put them however you want. I like raspberry ones, so we'll get a couple extra. 4, 5, 6, 7, 8, 9, 10, 11, 12. That's just one of the orderings, right? And then I could sort of arrange them all in a string. So how many things do I have written on the piece of paper not counting these edges? I have the donuts, plus I have one other thing on there that's important.
3 dividers.
I have the dividers that divide the columns. If I didn't have them on there, I'd be lost. I wouldn't know what to do. So I need to have those on there. So I need one less divider than I have kinds. So what I'm going to do is I'm going to make a string that has 15 things. And all I have to do is either choose where the 12 donuts go or the 3 dividers, because it's the same problem. So I could put my, and I'm not going to guarantee, I'll try to do the same thing. Let's see, 3 zeros, 4 of those, 3 of those. Oh, that's good, turns out, right? I just have to choose my 3 places for dividers, and then the rest get to be zeros. So what I have is I have the items that I'm choosing, plus dividers, and I can either choose the items or the dividers. It's a little less confusing to choose the items because I don't have to subtract anything from anything to get the number of items that I'm choosing. So dividers is 1 less than the number of kinds, and then my choices are just how many ways to put those ones in a bit string, where I make places for the dividers and the items. So this wasn't something that you should have been able to figure out by yourself. This was a clever idea that someone came up with that helps you solve these kind of problems. But what you should be able to do is when you recognize a problem that has order does not matter and it has replacement, that it is a divider problem. Right? So if I tell you that I get 3 trick-or-treaters coming up to my house and I have 3 kinds of candy to give out, you see the word kinds and you can tell that you're only going to count, like, doesn't matter what kind, you know, like I can't tell the M&Ms apart, so its order doesn't matter, right? It's with replacement because I can't tell them apart, right? So this is a combination with replacement. I would have a divider for each kid. And I'm assuming I could tell the kids apart, right? So in this problem, if I couldn't tell the dividers, you know, the things in the dividers apart, then I'd have to divide out again by some ordering of the different categories, right? So that would be just groupings, different groupings, that it didn't matter which group was which. So you have to answer a couple of questions. Does order matter or not? Do I have replacement or not? And are there multiple levels to the problem, right? So what is the product rule for counting? If I have 2 independent choices or happenings or events, then the possibilities for them both happening is just a product of each one happening, right? So the number of ways to do the first one times the number of the second ways. And that's what we were drawing all these pictures assuming, right? We're using the product rule to make these pictures. So what is the inclusion and exclusion principle? If I have an either or, it tells me how many I have to have, right? If I have A or B, then the number of possibilities for
A.
that is A plus B minus the intersection, right? A intersect B. So that's a union rule also, the same as the union rule in set theory that we did. Okay, and the last thing, I'm just going to remind you a few points. Euler is for edges. I need to have, if I have an Euler circuit, I need to have all the edges in the graph in my circuit. And I need to start and end in the same place. And what is the criteria for finding an Euler circuit? All verts, even degree, right? That means I have an Euler circuit. If I have exactly 2 odds, then what? Then I have an Euler path. And it's very easy to find Euler circuits. You just start traveling along your graph and writing down the nodes that you visit until you've gone over all the edges. And just make sure you don't leave a place that you can't get back to. That's all. So then we have Hamilton circuits. Uses all the vertices exactly once, right? And it returns, the circuit returns to the same one that it started at. And this one's harder because it doesn't have like a simple criteria for it. But it's easy if it has little wings sticking out, right? If it has little wings, you know that you can't have a Hamilton circuit. And also, if you have like little subcycles that you have to go on, it can't have a Hamilton circuit. And most graphs, most small ones, it's easy to check if you have one. So what's an easy way to find, it's a long algorithm, but what's an easy way to find if you have a Hamilton circuit?
Try each path.
Try all the possible orderings of the vertices, right? So you can try all the possible orderings, and if there's any ordering that makes you get stuck somewhere and you can't leave the way it says you should, then that's not a Hamilton circuit. So you just check them all and see if any one of them is valid. So you can have Hamilton circuits in paths, and you'll just have to check something to see if you can do that. Okay, this is a traveling salesman problem, also NP complete. Remember that? Because it's not polynomial time. This is an exponential time, right? Because that's a permutation problem. Right? N factorial is the size of that algorithm, if n is the number of nodes. Then we have Kruskal's algorithm. And that one finds what for us? Finds minimum spanning trees. So Kruskal's needs to add n minus 1. Like if you start with just the nodes, you need to add n minus 1 edges so that it connects them all, right? And all you have to do is start adding from the minimum that's left, as long as it makes no cycle. And there are more than one solution to minimum spanning trees. So if you have edges that have the same weight, it's very possible to have more than one solution. So you pick a random one of the smallest weight. And every minimum spanning tree has the same weight. And you can try it yourself with a couple of graphs and see what happens. That's pretty much it. And we'll see you next time for the test. And thank you for taking the course. I really enjoyed it. I hope you guys did too.